It's a birthday party, and someone's just opened a pack of balloons. Within minutes, someone inevitably grabs one, breathes in the helium, and starts talking. What comes out is instantly recognizable, a high-pitched, squeaky voice that sounds like a cartoon character. Everyone laughs. It's become such a universal party trick that most people have either done it themselves or seen someone else do it. But here's the strange thing. If you stop and think about what's actually happening, it makes no sense at all. You're breathing in a gas, and somehow that gas temporarily transforms your voice into something completely different. It feels almost like magic, as if the helium is reaching down into your throat and physically changing how your vocal cords work. But that's not what's happening at all. The helium isn't touching your vocal cords in any meaningful way, and your voice isn't actually getting higher in the way most people think it is. What's really going on involves the physics of sound waves, the speed at which they travel through different gases, and a fascinating quirk of how human speech is produced and perceived. The helium voice effect is a perfect demonstration of acoustic physics hiding in plain sight, and understanding why it happens reveals something fundamental about how sound works in any medium. Let's explore, right here on History of Simple Things. The first thing to understand is what most people get wrong about the helium voice effect. When you hear someone talk after breathing helium, your immediate impression is that their voice has become higher pitched, like someone turned up the frequency knob on their vocal cords. This seems logical, and it's what almost everyone believes is happening, but it's not actually true. The fundamental frequency of your voice, the pitch produced by your vocal cords vibrating, doesn't change at all when you breathe helium. Your vocal cords are physical structures made of tissue, and they vibrate at a frequency determined by their tension, mass, and length. Helium doesn't change any of those properties. If you could somehow measure the vibration frequency of someone's vocal cords before and after breathing helium, you'd find it's nearly identical. So if the pitch isn't changing, why does the voice sound so different? The answer lies not in the vibration of the vocal cords themselves, but in what happens to the sound after it leaves the vocal cords, as it travels through the vocal tract and emerges from your mouth. To understand this, we need to talk about how human speech actually works. Your vocal cords, located in your larynx, are the primary sound source. When you speak, air from your lungs pushes through the vocal cords, causing them to vibrate and produce sound waves. But the sound that comes directly from the vocal cords is not what you hear as speech. It's more like a buzzing sound, a fundamental frequency with a rich set of harmonics. What transforms that buzz into recognizable speech is your vocal tract, the complex three-dimensional space formed by your throat, mouth, tongue, and lips. The vocal tract acts as a resonator, a bit like the body of a guitar or the tube of a trumpet. Just as a guitar string by itself would sound thin and weak, but becomes loud and rich when attached to the guitar's body, the sound from your vocal cords becomes shaped and amplified by the spaces in your vocal tract. These spaces have natural resonant frequencies called formants, and it's the formants that give your voice its characteristic quality and allow you to form different vowel sounds. Here's where helium comes in. Formants depend on the resonant properties of the vocal tract, and those properties depend on the speed of sound in the medium filling that space. Under normal circumstances, your vocal tract is filled with air, and sound travels through air at approximately 343 meters per second at room temperature. But helium is very different from air. Helium atoms are much lighter than the nitrogen and oxygen molecules that make up air. A helium atom has an atomic mass of about 4, while a nitrogen molecule is 28 and an oxygen molecule is 32. This dramatic difference in molecular mass has a profound effect on how fast sound can travel through the gas. In helium, sound travels at approximately 965 meters per second, nearly 3 times faster than in air. This isn't a small difference. It's a fundamental change in how acoustic energy propagates through the medium. When you breathe in helium, you're temporarily replacing the air in your vocal tract with a gas where sound travels much faster. This changes the resonant frequencies of all the spaces in your throat and mouth. Think about how a pipe organ works. A long pipe produces a low note, and a short pipe produces a high note. This is because the resonant frequency depends on the length of the resonating chamber. But resonant frequency also depends on the speed of sound in the medium. If you could somehow increase the speed of sound inside an organ pipe without changing its length, the pitch it produces would go up. That's essentially what happens in your vocal tract when it's filled with helium. All of your formants, the resonant frequencies that shape your voice, shift upward proportionally to the increase in sound speed. The first formant might shift from 500 Hz to 1400 Hz. The second formant might shift from 1500 Hz to 4200 Hz. These are the frequencies that your brain uses to identify vowel sounds and voice quality, and when they all shift upward together, your voice sounds dramatically different. The reason it sounds high-pitched rather than just different has to do with how our brains interpret speech. We're incredibly sensitive to formant patterns because they're essential for understanding language and identifying who's speaking. When someone's formants are much higher than normal, our auditory system interprets this in a specific way. Higher formants are typically associated with smaller vocal tracts, which is why children who have physically smaller throats and mouths naturally have higher-pitched voices with higher formants. When an adult breathes helium and their formants shift upward, their voice takes on qualities similar to a child's voice or a cartoon character. Our brains don't consciously think, those formants have shifted to higher frequencies. Instead, we perceive it as the person sounding squeaky, chipmunk-like, or comically high-pitched. It's a perceptual illusion based on how we've learned to interpret acoustic patterns throughout our lives. This phenomenon works with other gases too, and the effects can be equally dramatic but in the opposite direction. Sulfur hexafluoride, often called SF6, is a gas that's much denser than air. Its molecular mass is about 146, making it roughly 5 times heavier than air. When you breathe SF6, sound travels through it at only about 133 meters per second, much slower than in air. This causes all your formants to shift downward, and your voice takes on a deep, booming quality that sounds almost demonic or otherworldly. It's the same physics working in reverse. The fundamental frequency produced by your vocal cords stays the same, but the resonant characteristics of your vocal tract change dramatically because sound is propagating through the space at a different speed. Demonstrations of SF6 are less common than helium demonstrations because SF6 is denser than air and tends to pool in your lungs, making it harder to expel naturally. You need to physically lean forward or even turn upside down to get it out, which makes it more dangerous if not done carefully. The physics behind why sound speed changes with molecular mass is rooted in how gases transmit acoustic energy. Sound waves in a gas are pressure waves, regions of compression and rarefaction traveling through space. When a molecule is pushed by the wave, it collides with neighboring molecules and transfers energy to them, propagating the disturbance. In a gas with lighter molecules, the molecules move faster at any given temperature because temperature is essentially a measure of average kinetic energy, and lighter molecules must move faster to have the same kinetic energy as heavier ones. These faster-moving molecules can transmit disturbances more quickly. Additionally, lighter molecules collide more frequently because they're zipping around faster. The combination of faster molecular motion and more frequent collisions means that pressure disturbances propagate through the gas more rapidly. The mathematical relationship is described by the equation for the speed of sound in an ideal gas, which depends on the gas constant, temperature, and molar mass. As molar mass decreases, speed of sound increases, and helium has one of the lowest molar masses of any gas. There's another factor that contributes to helium's extreme effect, the specific heat ratio of the gas. This is the ratio of heat capacity at constant pressure to heat capacity at constant volume, and it affects how efficiently the gas can store and release energy during compression and expansion. Helium, being a noble gas with single atoms that don't form molecules, has a higher specific heat ratio than air. This means it responds more stiffly to compression, which also contributes to the faster sound speed. The combination of low molecular mass and high specific heat ratio makes helium particularly effective at increasing sound speed, which is why the helium voice effect is so pronounced compared to other light gases. Interestingly, the helium voice effect has some practical applications beyond party tricks. In deep-sea diving, divers who descend to extreme depths breathe special gas mixtures called heliox, which is a blend of helium and oxygen. Nitrogen, which makes up most of the air we normally breathe, becomes narcotic at high pressures, causing a dangerous condition called nitrogen narcosis that impairs judgment and coordination. Helium doesn't have this problem, so it's used as a substitute for nitrogen in deep diving. But one side effect is that divers' voices become almost unintelligible due to the extreme shift in formants. At depths where the pressure might be 10 or 20 times atmospheric pressure and the breathing gas is mostly helium, voices become so distorted that normal communication is nearly impossible. This led to the development of special voice unscramblers, electronic devices that analyze the diver's speech, identify the shifted formants, and mathematically shift them back down to normal ranges so surface crews can understand what the diver is saying. It's a fascinating application of signal processing to solve a problem created by physics. Helium's acoustic properties are also useful in scientific research and engineering testing. Because sound travels so much faster in helium, researchers can use helium-filled chambers to study acoustic phenomena at higher frequencies or shorter timescales than would be possible in air. Some musical instruments have been tested in helium atmospheres to better understand their acoustic properties. Wind tunnels sometimes use helium mixtures to study aerodynamics at conditions that simulate different atmospheric densities, and helium is used in some types of acoustic imaging and medical diagnostics where its unique properties provide advantages over air. But there's an important safety consideration that needs to be addressed. Breathing helium is not entirely harmless, despite how common the party trick has become. Helium is an inert gas, meaning it doesn't react with your body or cause toxicity in the way that, say, carbon monoxide would. But it also doesn't contain oxygen, which your body absolutely needs to survive. When you take a deep breath of pure helium, you're filling your lungs with a gas that can't sustain life. If you take multiple breaths of helium in succession without breathing normal air in between, you can cause oxygen deprivation, which can lead to dizziness, loss of consciousness, and in extreme cases, death. There have been tragic cases of people, particularly teenagers, who suffocated after breathing helium from tanks or sealed bags without understanding the danger. The problem is that your body doesn't detect lack of oxygen directly. What triggers the urgent sensation of needing to breathe is the buildup of carbon dioxide, not the absence of oxygen. Helium doesn't build up carbon dioxide, so you can be suffocating without feeling like you need air. This makes it particularly dangerous. The safe way to do the helium voice trick, if you choose to do it at all, is to take a single small breath from a balloon, speak immediately, and then breathe normal air. Never breathe multiple consecutive breaths of helium. Never breathe directly from a pressurized tank, which can also cause lung damage from the pressure, and never breathe helium in an enclosed space where oxygen might be displaced. The effect is temporary and wears off within seconds as you breathe normally and the helium diffuses out of your lungs and is replaced by air. It's not worth risking your health or life for a brief moment of entertainment. The science of how gases affect sound also explains some other curious phenomena you might have encountered. Have you ever noticed that your voice sounds different when you're congested with a cold? That's because the mucus and swelling in your nasal passages and sinuses change the resonant properties of your vocal tract, shifting formants and altering voice quality. The same principle explains why your voice sounds different when you pinch your nose closed, when you speak while breathing through a snorkel, or when you talk inside a pressurized helmet. Any change to the geometry or the medium of your vocal tract will affect the resonances and change how you sound. Professional singers and voice coaches are acutely aware of these effects and spend years learning to control the shape and tension of their vocal tract to produce specific timbres and tones. The helium voice phenomenon is also a beautiful demonstration of the difference between frequency and timbre. Most people conflate these two concepts, thinking they're the same thing, but they're actually distinct properties of sound. Frequency refers to how fast something vibrates, measured in cycles per second or hertz. Timbre, on the other hand, is the quality or color of a sound, determined by the pattern of harmonics and formants present. Two instruments can play the same note at the same frequency, but sound completely different because they have different timbres. When you breathe helium, your fundamental frequency stays the same, your vocal cords are vibrating at the same rate, but your timbre changes dramatically because the formant structure shifts. This is why the helium voice sounds so strange. It's like hearing someone play a familiar melody on an unfamiliar instrument. The notes are right, but something essential about the sound has changed. Understanding the helium voice effect also helps us appreciate the incredible complexity of human speech. We take it for granted that we can produce dozens of distinct sounds just by changing the position of our tongue, the shape of our lips, and the configuration of our throat. But each of these adjustments is creating a different resonant chamber with different formant frequencies, and our brains have learned to recognize these patterns with extraordinary precision. We can identify individual people by their voice alone because each person's vocal tract has a unique size and shape that produces a characteristic formant pattern. When helium shifts everyone's formants upward, it disrupts these identifying features, which is part of what makes helium voices sound so funny and unnatural. We're hearing familiar voice patterns shifted into unfamiliar acoustic territory. So the next time you hear someone do the helium voice trick at a party, you'll know there's far more going on than just helium makes your voice high. You're witnessing the physics of sound propagation, the relationship between molecular mass and wave speed, the resonant properties of acoustic chambers, and the complex way your brain interprets formant patterns to understand speech. You're seeing a demonstration of how the same physical principles that govern pipe organs and wind instruments also govern human speech. And you're experiencing how something as simple as changing the gas in your vocal tract can create such a dramatic and instantly recognizable effect. It's a reminder that physics isn't just abstract equations in textbooks. It's everywhere, in the most ordinary and entertaining moments, quietly governing how sound moves through space and how we perceive the world around us. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution.